Last time I described to you the null result of the Michelson-Morley experiment. The Michelson-Morley experiment failed to detect the presence of the ether. It failed to detect specifically the motion of the Earth through the ether. That was a huge hole that existed in physics at the time, because according to what was understood at the time, the experiment should work, and it should work easily. Yet the experiment failed. Nobody could explain satisfactorily why the experiment failed to detect the presence of the ether. Not for about 20 years. And now we get to 1905 with Albert Einstein. In 1905, Albert Einstein is 26 years old. He has an undergraduate degree in physics. However, while he was in college, he made a mistake. Don't make this mistake. The mistake that Einstein made while he was in college was that he alienated his professors. Quite frankly, he was an arrogant jerk. And because of this, those professors would not write him the necessary letters of recommendation that he needed to go on to graduate school such that he could obtain a PhD in physics, which was his goal. However, with a young family to support, what did he then do? Well, he did what anybody would do. He took a job. His job was actually to work in the Swiss Patent Office as a clerk. And basically, he would sit at a desk from 9 to 5, and he would look at the various designs of various gizmos and so on and so forth. And then based upon the design, he would then decide whether or not to grant that person a patent. Here was Einstein's approach, by the way, to his job. Basically what he would do is he would look at the design of whatever it was and determine whether or not it violated the laws of physics. And then therefore, if it did, of course it would not work, and then therefore he would not grant the patent. However, while he was working this 9 to 5 job, he was also working on physics himself on the side. And he discovers, or he notices, that there are deep inconsistencies that lie at the heart of classical physics. You can summarize those inconsistencies in the following way. For example, if the ether exists, it actually violates Newton's first law, the law of inertia. Because remember what the law of inertia says. It says that there is no physical difference between an object at rest, constant velocity of 0, and an object moving in a straight line at a constant speed. That's also a constant velocity. In other words, the two situations are both inertial reference frames. However, the idea of the ether says that there is a difference between being at rest and being in motion with respect to the ether, and the Michelson-Morley experiment was designed to detect that difference. For my AP students, recall the equations of electromagnetism, and then recall what Maxwell did. He mathematically combined those expressions together, and he derived the speed of light, 3 times 10 to the 8th meters per second. When you combine the equations together in this manner, there is no reference frame stated. At the time, in the 1860s, Maxwell merely assumed that what he was deriving was with respect to a stationary observer. But when you try to apply the equations of Galilean relativity to electromagnetism, they don't work. That's another inconsistency that Einstein notices. So that's basically his approach to the problem associated with the ether. If you assume it exists, it leads to all of these contradictions. However, Einstein discovers that if you make 2 assumptions about nature, all of those inconsistencies disappear. These assumptions are referred to as the postulates of special relativity. Okay, now the word postulate in scientific lingo means it's an assumption. We're going to assume that nature works this way and then go from there. The first postulate is basically just restating Newton's first law, but giving it considerably more emphasis. The first postulate is that the laws of physics are the same for all inertial reference frames. Now remember that an inertial reference frame is a reference frame at a constant velocity. This is basically saying that there is no physical difference between being at rest and being in motion in a straight line at a constant speed. Both are inertial reference frames. However, he's essentially giving the idea here of Newton's first law considerably more emphasis. Here's a nice, easy conceptual example to use to wrap your head around the first postulate. Let's consider the classroom here to be an inertial reference frame. And then, just as we did earlier in the year, let's say that we do an experiment involving conservation of momentum. Recall the one-dimensional collisions experiment that we did where our two air-track carts collided together and they stuck together. Basically, what we did in that experiment was as follows. We totaled up all of the momentum of the system before the collision, we totaled up all of the momentum of the system after the collision, and the two were the same. In other words, momentum was conserved. Now imagine doing that same experiment on a train. Well, let's say that the train is moving at a constant speed in a straight line. It's at a constant velocity, so then therefore it's an inertial reference frame. So you then conduct the experiment. You total up all of the momentum of the system before the collision, you total up all of the momentum of the system after the collision, and they're the same, conservation of momentum. In other words, the laws of physics, in this case, conservation of momentum, are the same in both of those reference frames. So once again, it's basically just restating Newton's first law, but giving it considerably more emphasis. It's the second postulate, however, where things get strange. The speed of light is the same for all reference frames, inertial and non-inertial. Here's what this postulate is saying. Go all the way back to the first semester, for example, with our conceptual example that I used with Galilean relativity. Consider yourselves to be a stationary reference frame. Let's say that I'm in a starship and I'm moving towards you at half the speed of light. And let's say that right here in my hand I have a laser and I shoot the laser at you like so. According to me, the laser light itself leaves my hand at the speed of light. However, if you use Galilean relativity, according to you, you would see the speed of the laser light as 1.5 times the speed of light. No, instead, you see it at the same speed of light as I do. Or consider the following situation. Let's say I'm in that same starship, but in this case, I move away from you at half the speed of light. And then I turn towards you and I shoot the laser at you like so. According to me, the light leaves my hand at the speed of light. Using Galilean relativity, according to you, you would see the speed of the laser light as 1/2 the speed of light. No, you see it at the same speed of light, even though we are both moving relative to each other. Now that sounds strange, but if you think about it carefully, the null result of the Michelson-Morley experiment is experimental verification of the second postulate of special relativity. Because basically what the experiment is doing is it's measuring the speed of light. So for example, let's say that we do the experiment here in this room. And when we do, the light beams go out, hit their mirrors, and come back at the same time. What we just did is essentially we've measured the speed of light. Now imagine doing the experiment on a starship. And let's say that that starship is moving at 90% the speed of light relative to the Earth. However, it's just another inertial reference frame. It's as if we're just standing here in this room. And then we do the experiment again while we're on the starship. The light beams go out, hit their mirrors, and then come back at the same time. We've measured the exact same speed of light in the two different reference frames. Think of it in terms of the conceptual example that I used earlier about the Earth orbiting the sun. Let's say that the Earth is orbiting the sun like so, with an orbital speed of 30 kilometers per second. And then boom, right here at this moment where we're moving in that direction relative to the sun at 30 kilometers per second, we do the experiment. Light beams go out, hit their mirrors, and come back at the same time. We just measured the speed of light. And then 6 months later, we're on the other side of the sun like so, in a totally different reference frame. moving in the opposite direction relative to the sun at 30 kilometers per second, and we do the experiment again, and we get the exact same result. The two light beams go out, hit their mirrors, and come back at the same time. We measured the exact same speed of light in the two different reference frames. At the time, nobody understood the implications of this result, but Einstein realizes that the null result of the Michelson-Morley experiment is experimental confirmation of the second postulate of special relativity. Now, the consequences of these postulates are bizarre. We'll take a look at that in part 2 of the videos for today.